Thank you, Mrs. Chairman, and thank you for inviting me. Can you hear me?
Yes, everything is okay.
Thank you.
Everything's okay. So thank you. I'll try to share my screen. I'm the last one. I'm the last speaker, and I guess you are hungry. So I'll try to do my best because my presentation is long. But anyhow, if the time goes without finishing it, please interrupt me. So it is available. You can see the presentation at this link here. I'm starting with the mainstream climate narrative, which is has as a core the causal link that you see. We have the human CO2 emissions, which increase the atmospheric concentration of CO2, and then this results in global warming. And then we have several climate impacts, which means impacts of the CO2 emissions. And these impacts are on everything, from hydrology to kidney stones. I guess you have seen papers relating climate with kidney stones. I believe that this view is naive and simplistic, reflecting kindergarten level science. I agree with another speaker who used this term before. It is promoted, of course, by IPCC and the political and economic interests, particularly those of the controlling oligarchs. And what puzzles me is that it is also supported by the majority of skeptics, who I call mainstream skeptics. And I have had differences, and I have been arguing with the majority of skeptics because I think they argue about the climate edifice focusing on the penthouse. And as you know, I am working in the School of Civil Engineering, so I view this as an edifice, and I made a cross-section here on the right, and I believe that what we should study is the foundation before everything. And but usually the skeptics do not focus on the foundation. And my question is, why? Is the underlying science correct and only the details need to be discussed? Or should we prove that we are not bad guys? Or should we confess faith to the dogma that humans are responsible? Anyhow, I'm returning to the causal link, and I will examine each of the three links in three parts of my presentation. First, is the increase in atmospheric CO2 caused by human emissions? My reply is no. But the IPCC reply, of course, is yes, and yes is also the reply of mainstream skeptics, and I have been arguing with many about that. Can you hear me again? Because I
Yes, now you are online. Okay.
Okay. I think there was an interruption. Anyhow. I'm continuing with these two papers. The first one is about the isotopes, and the other one, the next one, is about the total dynamics of the CO2 in the atmosphere. So to start with the isotopic signature, this is the graphical abstract of the paper, and you see that during the last 40-something years, there is a decrease of the isotopic signature. This is a specific metric of the 13th isotope of carbon in the atmosphere, and you see this is decreasing. And the conventional explanation is that humans caused this decrease, as caused everything else, because they emit CO2. Okay, so on the one hand, we have this, which is the decrease of the atmospheric concentration of this isotope. On the other hand, we have the source of CO2 to the atmosphere, and this is not increasing. Probably it is increasing, not decreasing. So, and this happens also not only for the modern period, but the proxy data show that it happens the entire period after the Little Ice Age. And these observations support the conclusions that natural causes drove the CO2 increase. The human-caused signature, which is called Suez effect, is not discernible. And there is no logical basis in this effect. You see in this graph, here we have this metric, delta 13 carbon, and you see the atmosphere, the values in the atmosphere are between 7 and 9. The fossil fuels have lower, so it is reasonable to assume that when we burn fossil fuels, this will go down. But what happens is that the plants have even lower isotopic signature than the fossil fuels, and this happens also for other categories of emitters. So it is absurd to suggest that the emission from burning fossil fuels causes the atmospheric isotopic signature to fall. The second paper used some knowledge that we have in reservoir routing in hydrology. I am a hydrologist, and we have tried in hydrology to clarify the issues, which is just the opposite. As a sample here, I'm showing the definitions. This is in full contrast with IPCC, which tries to obscure every concept it uses. For instance, it says that the lifetime of the CO2 is multiple, and that simulations with climate travel cycle models show multi-millennial lifetime in the anthropogenic CO2 in the atmospheres. This replies to another question. IPCC uses different weights for human and for natural CO2. But of course, this is totally silly. No sense. So with this model, based on what we do in hydrology about water, I was able to reproduce exactly, almost exactly, the measurements of the atmospheric CO2. This is again the graphical abstract of the paper. The lower graph is the CO2 concentration, with green line is the measurements, and with red dots are the model results. This is comparison with measurements. The upper graph is also comparison with measurements. We know from measurements the net inflow minus outflow. This is known. So again, we have a very good agreement. And what we should observe here is that in the beginning, somewhere in the 60s, the seasonal variation was about 130 ppm per year in Barrow, and now it's 240. So there is an expansion of the biosphere, and this is fully reflected in that graph. So the results of this study is that the residence time of the CO2 in the atmosphere is independent, of course, of the origin, whether human or natural, is about 4 years on overannual basis, and within the year it can be lower up to 2 years because of the vegetation. The vegetation controls what happens in the atmosphere. And in this graph here, you see exactly the upper curve, the green curve, is the expansion of the biosphere. And usually the IPCC uses only this part of the graph, the red line here, and the pink line, and forgets the forest. And the forest contains all the forest, but also all the other organisms that live on Earth. And there is a big difference, as you see, from the scale. So the IPCC forgets this increase of expansion of the biosphere, which is 5 times more than the human emissions. But also the skeptics also focus on this part and forget the upper part, which they say are the biosphere is constant or is a response to change because of the atmosphere of the human emissions. My results fully agree with the carbon balance of the official carbon balance of the IPCC, which you see here. And you see in 2 colors. The one is what happened in the pre-industrial era, and the red bars are what happened after the pre-industrial era. So the expansion of the biosphere is reflected even in the balance, the official balance of IPCC. And I note here a very recent paper, a couple of weeks ago, has increased these 2 numbers here. So we have 9.4, the human emissions from fossil fuels and cement production, and we have 136.7 gigatons from natural causes only on land. And you should also add what happens in the oceans, and you should perhaps consider the new estimates, which are even higher. So that's about the first question. Let's go to the first link. Let's go to the next causal link. Does the increase in atmospheric CO2 cause temperature increase? Of course, the IPCC replies yes. The mainstream skeptics also reply yes, and I reply no. And here I have 5 papers about this issue. This is the first one, which was published in 2020. And the reason where we parallel these problems with the hen or egg notion of causality, I will explain. The trigger of our study, which is not just mine, you see it's by Professor Kunzevich as well, who is co-author, who is an IPCC leader, by the way. And you see that the emissions of CO2, the human emissions of CO2, went down significantly, the red line here, during the COVID lockdown. But there was no change in the atmospheric CO2. This graph is from that paper. That's why it stops in July 2020. This was our first paper. Then we published a couple of papers in Royal Society. And we supported this our proposal that we need to study causality in depth, because causality is a central concept in science, in philosophy, in economy, and it has become an arena of enormous interest. Eventually, we were able to publish them, and in these papers, we started from philosophy. Of course, causality was like almost any other philosophical and scientific concept was started by Aristotle, so I have to mention him. But also I would like to mention Plutarch, who put the problem of hen or egg type of causality, ornis ion, the Greek terms. And also he replaced the notion of events, which was the notion in Aristotle, with the processes. Because here you understand, when you see hen or egg, you speak about processes, not events. And that's very important. Big philosophers, Hume and Kant, also were involved with the problem of causality. but I will refer to modern ones, modern philosophers and mathematicians, starting with Sapes, who defined in a probabilistic manner causality, but we were not satisfied at all with this definition, and we proved in our paper that his definition identifies causality with dependence, which is not what we want. Then there is a British statistician in Oxford, David Cox, who completed Sapes' definition, but what he proposed is totally impractical because it says there is no event between the two that could influence, etc. You cannot enumerate all events that happened before that time. Then it's the Nobelist Clive Granger, who proposed a mathematical test, a statistical test, which has the name Granger causality test, but it's not a test about causality. It's a test about prediction, which is different from causality. And perhaps most famous in our period is Jude Appel, who proposed a framework that was heavily used for determining causality in climate, but it's wrong because he has two problems. The chain rule is inappropriately used, and second, he makes the assumption that we have already a causal graph, and if we have a causal graph, then no meaning to continue. So we proposed a totally different approach. We admitted that there are several unsolved problems in causality. We decreased our ambition. We cannot, and we say we cannot provide sufficient conditions for causality, but we can find necessary conditions. And this is our ambition, is to find necessary conditions. And this is important for both deductive and deductive reasoning. For deductive reasoning, we can falsify a hypothesis if we have a necessary condition. In inductive reasoning, we can add evidence in favor of the plausibility of the causality hypothesis. Our method is based on stochastics. We exclude what is the popular in silico experimentation, which uses models to identify causality. Of course, this is a circular logic, and we refuse that. And we started our framework with hen or n causality, and a special case which goes both ways. And as special cases of this hen or n, we have a causal or an anti-causal system. These are the mathematics of the area. You can see it as homework. These are our results. This is the impulse response function, which is a well-established notion in stochastics. And for the CO2 temperature problem, it has only values only on the positive semi-axis. This means clearly that you can exclude the case that CO2 causes change in temperature. And if you get the opposite relationship, you have all the coordinates of the positive axis negative. So the causality directions from temperature to CO2 is plausible. The other one can be excluded. Then, after the two papers in British Society, we published also another couple of papers. In the first one, we used multiple scales because we received a lot of criticism that this can happen for small scales, but not for round. And we proved that this is also the case for larger time scales. And we extended the study using also proxy data covering the entire Phanerozoic. This graph from the first paper, from this paper here, multiple scales, makes this trick here. We take annual time series of temperature and of CO2, but lagged by 6 months. 6 months is halfway between 0 and 12 months. Okay. So you see here, if the CO2 were the cause of the temperature increase, you could see this point, this green point that I'm showing now would be 6 months before, not 6 months after. And if you see in this depiction of the same thing, you see when you consider temperature as a cause and CO2 as an effect, you have a correlation coefficient of 0.75. If you do the opposite, you have a correlation coefficient of 0.01. And again, the data I have used in proxy data that I have used for the entire Phanerozoic, for the Cenozoic, late Quaternary, Common Era, and modern instrumental data. If you see the lungs, they are always positive in all time scales. Of course, there are cases where the two processes decouple, but generally, stochastically, we have always positive lungs. And it's very easy to understand why the lungs are positive. And just look at this couple of photos to the right. Here in the bottom, you don't have a lot of respiration. I hope you agree. In the upper photo, you have a lot of respiration. Living organisms love warm conditions and increase their respiration with temperatures exponentially. This is a typical mathematical equation, the exponential increase with temperature. And you see also data, measurements in forests in, I think it was in Japan, that show exactly this simple thing. This is one of the graphs that compares temperature and CO2. I do not have the time to explain. I'm going immediately to the last link. The last causal links. Are there climate impacts, or do human emissions affect everything? The IPCC and the climate zealous reply is yes. Some of the mainstream skeptics say yes, perhaps, but the majority says no, and I too reply no. Here I have a couple of papers again to find the relative importance of CO2 as a greenhouse gas, and to find this relative importance, I use as comparison the water vapor and clouds, which happens to be my area because these are part of hydrology. This paper on the right, on the left, which was published in Hydrological Sciences Journal, uses only data. And the other one uses satellite data and models. The data, the first paper, we have since the era of Axstrom, 1912 to today, we have lots of ground measurements of downwelling long wave radiation. So I took several of these data sets and plotted, and what I found is that the century-long collection of data, after being analyzed, show that there is no discernible effect of the greenhouse intensity, despite the increase of the atmospheric CO2 from 300 ppm to more than 400 ppm in a century. I do not have the time to explain in detail this graph here, which shows exactly this, and it shows based on data. The second paper used the Montran, the official theory of the greenhouse. Of course, I know that there are some who refuse this theory, but in this paper, we accepted this theory. We used the models that simulate what happens in the atmosphere. And of course, we used also the model results in comparison with the CERES, the NASA data of long wave radiation. I was able to make this macroscopic relationship, which has the influence in the downwelling and outgoing radiation of temperature, water vapor pressure, CO2, and clouds. This is an equation. I'll show you in a minute how good or bad this equation is. And if you have this equation, you can take the partial derivatives with respect to each of these variables, and this is the partial derivative, find the total derivative here, and you can split the influence of each of them into a percentage or whatever. So this is a comparison of Montrand results with the results of the macroscopic relation. You see perfect agreement, both without clouds or even with clouds. So, and then we can do this breakdown, and this breakdown results in this here, this pie graph here. 4% is the contribution of CO2 to the greenhouse, 50% is the water vapor, and 45% is the clouds. All other gases, 1%. This is for downwelling radiation. So this explains why in the first paper, this one, we didn't find any change in the greenhouse during the last 100 years. This, for the outgoing radiation, we don't have long data sets. We have only for the last 20 years, satellite data. Here, the 4% contribution of CO2 became 5%. So the CO2 is not the cause of everything, of anything. If the CO2 is not the cause, what might have caused the recent increase in atmospheric temperature? In our paper, we examined several possible causes like albedo, ENSO, ocean mean temperature, etc. And we found that indeed all these precede in time the changes of temperature and of course of CO2, which follows. So this graph here shows some possible connections, but I cannot reply this question. Instead of replying this question, I answer some more questions. Should we expect temperature to be stable? Do complex systems, complex dynamical systems need external agents to change their state? I have here a link to 3 papers of mine, which I have proved the opposite, that such complex systems can change by themselves their status. They are not dead. They are alive systems, and alive systems means they change. Okay, another question. What caused a cause? And another question. Have the huge changes in global temperature during the Phanerozoic been explained? As a hydrologist, of course, I focus on albedo, so I did some more analysis here. You see a graph from the paper of 2023 and one from 2024. Here is the albedo, and there is a decreasing trend in the last 20-something years, a decreasing trend which translates to 1.4 watt per square meter. And this is much greater than the calculating from the heating of the oceans, which in my calculation is 0.4. This imbalance, let's say, is 0.4 watts per square meter. And only the decrease of albedo is much higher. And why the albedo decreased because the cloud area fraction decreased. And this graph shows it clearly. And again, all these graphs are from data. So to conclude, the mainstream causal chain in human emissions, increased atmospheric CO2, global warming, climate impacts. I have tried to reverse the change and to the link and first replace the impacts with drivers, hydrology and other climate drivers. Change produce global warming, change the temperature, and the temperature change increases the atmospheric CO2. And yes, we have also some human emissions that do the same as the natural causes. So we have here two coincidence of two different causes that have the same result. What can we have the percentage of the two? Yes, I have tried to calculate that it's 17% for human emissions, 83% for the natural causes. Final remarks, the foundation of modern climate edifice is afflicted by erroneous assumptions and speculations. The causal change promoted by mainstream science and sometimes supported by skeptics is naive and wrong. In scientific terms, the case of magnified importance of CO2, particularly that of human emissions, and the neglect of 25 times higher grade, higher natural CO2 emissions constitute a historical accident. This accident was exploited in non-scientific political economic terms, mostly dark ones, I mean the quadroligarchs here. For complex systems, observational data are the only scientific test bed for making hypotheses and assessing their validity. I would never trust climate models for whatever. The real-world data do not agree with the mainstream science, which is a euphemism for sophistry. The results that I have presented are scientific, I believe, and therefore may not be relevant to the climate narrative, which has a non-scientific aim. Thank you very much.